So the previous module, we talked about algorithms and the resources that they consume. And we saw in this MATLAB example where we added one number at a time to a list that sometimes there can be surprises. And in this module, we're going to talk about orders of growth. And we're specifically going to talk about how sometimes something slightly surprising dominates. And because of that, we need to focus on the dominating aspect. So let's look at two different types of sorting algorithms. The first one is called an insert sort. And in the insert sort, you maintain a sorted list of numbers processed so far. And the next item is going to get sorted, or rather inserted into your list. And one by one, you add things to your list. So let's here give an example. So my list is going to be, the numbers will be 5, 2, 3, 6, -5, 8, let's say 7, and 0, okay? So step 1, I put 5 in the list. That's it, it's the first number. Step 2, I look at my list and I look at the number 5 and I put, I look at the number 2 and it comes before 5. I'm going to put an asterisk next to the 2. That's my new number. I put it before 5. 2 and 5 are now sorted in my list, and the next number is the 3. So I have 2 and 5, and I'm going to put the 3 between them, okay? Just to keep it simple, I'll double asterisk. And now what about step 4? So I have 2, 3, and 5. The next number is a 6. 6 belongs at the end of the list, after the 5. Now we discussed earlier that if we're just growing the list one element at a time, that may be foolish, but suppose that we saw that whatever number of elements here there are, 7, 8, whatever, we initialize our list to be of the same size. So we don't have that issue. So one by one, we add numbers to the list. Step 5, we have a -5, 2, 3, 5, 6. And the -5 goes to the beginning. And then in step 6, and I copied what I just had, the next number is the 8, and the 8 appears at the end. Step 7, the 8 appears at the end. The next number is a 7, which occurs right between the 6 and the 8, so close to where we were. And finally, step 8, I have a 0. So -5, 0 is right after the -5 and before the 2. 2, 3, 5, 6, 7, 8. Now, of course, I was assuming here that all the numbers to begin with were integers. Maybe that helped me, maybe not, depends on the technique. I was assuming that all the numbers are different. If I have two identical numbers, maybe the 3 appears twice. That may change things just a bit, but overall, this is intuitive and clear to us. Now, what about the merge sort? We divide the problem into 2 parts, and they're supposed to be the same size. And if we have 8 numbers in the list, which was in our example, not a problem. 8 becomes 4, 2 parts of size 4. And then after dividing into 2 parts of size 4, we conquer each problem, which means that this merge sort, we're going to recursively run problems of size 4, and then we merge the solutions. So now, in the merge sort, so we start with sorting a size 8 problem. We partition into 2 problems, each of size 4. We recursively solve each, merge two solutions of size 4. Now, for now, suppose that 4 is small enough, we just run it, okay? Suppose that 4 is solvable by force. Force meaning, whatever method you want, including insert sort. So now let's work through our example. So we have our list. We have 5, 2, 3, 6, -5, 8, 7, 0. We partition into list 1 is 5, 2, 3, 6. List 2 is -5, 8, 7, 0. Sort of list 1. Let's assume that this is fast. So 5, 2, 3, 6 becomes 2, 3, 5, 6. And sort of list 2 is -5, 0, 7, 8. And now the merge of 2, 3, 5, 6 and -5, 0, 7, 8. So now think about it. Imagine that I have cards. I have 2 decks of cards. One deck of cards, the numbers 2, 3, 5, 6 appear one beneath another. The other deck of cards, -5, 0, 7, 8. I look at these 2 decks of cards. All I'm seeing is the top card. So 2 decks of cards. Tops are 2 and 5, the tops of the decks. And I put aside the smallest. 0, 5 is the smaller. And the remaining decks are 2, 3, 5, 6, and 0, 7, 8. And then the new one is -5. In the next step, I'm looking at 2, 3, 5, 6. The first one is 2. I'm looking at 0, 7, 8. The first one is 0. 0 is smaller than 2. I put the 0 in my new deck after the -5. So now I have 2, 3, 5, 6, 7, 8, and the new one is -5, 0. What about the next step? I'm looking at 2 and 7. 2 is smaller than 7, and therefore I move the 2 to the end of the new deck of cards. 3, 5, 6, 7, 8. And the new deck of cards is -5, 0, 2. And I leave it to you guys to do this at home, guys and ladies, of course. And you can see that overall, the merging step is proportional to n. The number of steps, I had 2 decks of cards. Each of them had half of n cards. In my example, it was exactly half of n because n was 8, half of n was 4. Assume close enough to half. Half of n or half of n plus half or half of n negative half, doesn't matter, details. If I have 2 decks of cards of roughly half n each, the merging step, n times I look at the 2 decks of cards. I look at the first element, I do a single comparison, who's smaller, I put my smaller one at the end of the new deck of cards, and that's it. So n times I perform simple steps, proportional to n. Now you could tell me at this stage, hey, what about sorting the problems of size 4? So now let's sketch this. I'm beginning with a problem of size 8. I partition it into 2 problems of size 4. Suppose that they're hard to solve. So I partition each of them into 2 problems of size 2. And now I can partition each of those into a problem of size 1. And I think that all of you know that a problem of size 2 is trivial. So that last level of partition, I'll put this in another color. This was really, I put an X over it, not needed. But hypothetically, in a more complicated algorithm, maybe problems of size 2 are difficult. So we can recursively solve smaller and smaller problems, and as long as my merge is efficient, we're done, okay? What's really taking the runtime is the merge. The conquering is done recursively with the basis step for the smallest problem, which works in a reasonably fast fashion. That's going to work any way you want, and the merges are going to take the runtime. We're going to merge 2 problems of size 1 into a problem of size 2. We're going to merge each of these problems of size 2 into a problem of size 4, and so on. All right. So let's move to the next slide. And I see that I should have deleted my drawings. That's fine. So in the next slide, I was supposed to run insert sort and merge sort on whatever the example was. Is it a different example? We get it by now. No problem. So we ran it. What about the running time? So let's discuss a problem of size n where now n will be a lowercase number, and we're going to denote the running time by t of n. And insert sort is going to be t subscript I of n, I for insort. And merge sort will be t subscript m of n, merge sort with an m. Ti of n will be proportional to n squared. Now, proportional to n squared may be 7n squared, a 7th n squared, whatever. Merge sort will be n log n. And now let's give insert sort an edge. So if my merge is implemented by a bad programmer, maybe the insert sort takes 100 n log n operations. I'm sorry, the merge sort is 100 n log n, and the insert sort is exactly n squared. And maybe not only that, the insert sort runs on a cluster, 1 trillion floating point operations per second, or not necessarily floating point, 1 trillion instructions per second. And my merge sort is going to be on a regular machine, 1 billion operations per second. Now, I could squeeze this further. We could be running on an abacus with 1 operation per second, but let's not exaggerate, okay? So I gave the insert sort 2 edges. A bad programmer for the merge sort, and the insert sort is running on a much faster computer. So let's see what happens. For problems of size 1,000, the merge sort takes 100 n log n operations, log base 2 of n, and it performs 1 billion operations per second, and 100 times 1,000, and what's log of n? Log base 2 of 1,000 is approximately 10, so 100,000 times 10 is approximately 1 million. 1 million divided by 1 billion is 1,000th of a second, a millisecond. What about the insert sort? N squared, but I'm getting 1 trillion operations per second. N squared is 1 million. 1,000 squared is 1 million. 1 million divided by 1 trillion is 1 divided by 1 million, which is a microsecond. So for a problem of size 1,000, this merge sort takes a millisecond. The insert sort takes a microsecond. Yeah, it's way faster. What about a problem of size 1 million? The merge sort takes 100 n log n operations. Log base 2 of 1 million is roughly 20. 100 times 20 is 2,000. 2,000 times 1 million is 2 billion. 2 billion divided by 1 billion operations per second is 2 seconds. What about the insert sort? So I square the million, that's 1 trillion. 1 trillion divided by 1 trillion operations per second is 1 second. So take a look at where we are now. We started with, for a smaller sized problem, the insert sort was way faster. For medium-sized problem, size 1 million. Comparable. But now let's move to a large-sized problem. The merge sort, 100n log n. So log base 2 of a billion is approximately 30. 100 times 30 is 3,000. 3,000 times a billion is 3 trillion. And 3 trillion divided by a billion instructions per second is 3,000 seconds, 50 minutes. It's manageable. So you're running it on a normal computer. You have a bad programmer. It runs in less than an hour. It's okay. What about insert sort? N squared is 10 to the 18 divided by 10 to the 12 operations per second is a million. A million is about 11 days. An hour is manageable. 11 days, well, depending on the application, I think you're starting to see my point. I'm saying that I gave the insert sort every possible edge. I gave the merge sort a terrible programmer. I gave the insert sort a wonderful cluster. And all of a sudden, the insert sort is running a lot slower. So asymptotic growth matters. And what I was trying to say in this segment of material is that we want to characterize the order of growth. So when we're looking at T of n, the runtime, which is an squared plus bn plus c, a, b, and c are positive constants. Asymptotically, the an squared matters. The b and the c, maybe b is a very large constant, and maybe c is a hugely large constant. For practical problem sizes, maybe the b and c matters. For larger problems, sooner or later, the an squared is going to dominate. So what we are going to try to do in the next module is to characterize the asymptotic rate of growth for larger size problems. And this leads to notions of theoretical complexity of resource consumption, computational complexity. So that'll be all for this module, and we'll continue.